Hello, students. This is a lecture on chapter 17, the nature of stars. The main points you should focus on while going through this chapter are how can we measure the distances to the stars, how we measure a star's brightness and luminosity, the magnitude scale for brightness and luminosity, how a star's color indicates its temperature, how a star's spectrum reveals its chemical composition, how we can determine sizes of stars. There's a different kind of diagram called Hertzsprung-Russell diagram, which are called HR diagrams for short. We'll learn about those. We will talk a little bit about binary stars as well. All right, so let's start with the first point, which is how can we measure distances to stars? And so the answer to that question is that we measure distance to stars using a phenomena called stellar parallax. So parallax is this effect where if a person is standing in one position, in position A, then the tip of the tree appears to be in front of one mountain, whereas if you are standing at position B, then the tip of the tree appears to line up with the other mountain. So that means because of change in position of the observer, the closer object seems to move against the background. This concept phenomena is used to determine the distances of some of the closer stars. So what happens is that as we are looking at the sky and taking uh, very good measurements, and as the Earth moves, changes its position from January to July, getting from one end of the orbit to the other end of the orbit, this movement of our observing position causes a parallax effect on the nearby stars. And by measuring the angle of the parallax, we can determine the distance of the stars. The formula for calculating that is very simple. D is equal to 1 over P, where distance is in parsec and the angle is in arc seconds. So, for example, if you want to find the distance of a star whose stellar parallax is 0.25 arc seconds, then you would do a reciprocal of it, and 0.25 is a quarter, and when you do a reciprocal of it, it will be 4. So the distance of this star will be 4 parsec. So we can do these measurements by using telescopes on Earth, but even better measurements can be done by sending out telescopes in the space. The further away the stars are, the smaller is the parallax. So in order to determine the distances of faraway stars, we need more precision. We need instruments which can measure smaller and smaller angles accurately. And for that, we need to get outside the atmosphere of Earth and in space. So there was this this telescope that was sent to space. It was called Hipparcos, High Precision Parallax Collecting Satellite. So for all the known stars, the angle of parallax is less than 1 arc second. That means that all of them are further away than 1 parsec. Now, Earth-bound telescopes, the most precise, the smallest angle that they can measure is 0.01 arc second. So that puts a limit on the maximum distance of 100 parsec. We can only determine the distance of stars as far from us as 100 parsec, any further, and we cannot. But by sending this Hipparcos, the resolution is 0.001 arcsecond, which increases the distance to 1,000 parsecs. Further than that, it's difficult to measure the distances using parallax, so we use other methods, which will be discussed in another chapter. As far as measuring the velocities of the stars, they are measured by a variety of methods. One is simply tracking its movement, and the other is using Doppler or other such methods. So the velocity of a certain star can be broken down into two parts. One is the radial velocity, which is directly in line with the line joining the Earth and the star. And the other is the tangential velocity, which is perpendicular to that line. If we can determine both of those, then we can get the velocity of the star. So the tangential velocity can be measured by observing the star over a long period of time and seeing how it is moving laterally, such as shown in the next slide. Barnard's star has been moving against the background. As far as the radial velocity, the Doppler method works very well for this. Luminosity and apparent magnitude scale. The brightness of stars is measured in a unit which is called magnitude. So this system was developed by a Greek mathematician whose name was Hipparchus. And the way it started out was he went and looked at the sky and the brightest stars that he could see. He gave them a rank 1 or a magnitude of 1. And then there was a second magnitude which was less bright, and third magnitude was even less bright, and so on. So he developed a system where the lower the number, it's more like a rank. The lower the number, the more bright the star is. Later on, as technology developed, it was possible for us to measure much more range of the brightness and as well as uh, differentiate different radii, different brightnesses. And so this was made into a continuous scale in which lower numbers represent more brightness. So for example, Venus or Sirius, which is the brightest star, has a magnitude of minus 1.4. And Venus at its brightest has a magnitude of minus 4.4. But most stars fall somewhere between 0 and 5. And in fact, the naked eye limit is 6. Any star which is 6 or a higher magnitude, we cannot see with our eyes. Binocular limit is 10. And the Hubble Space Telescope limit is 30. What is luminosity? Luminosity is a measure of star's total light output. I think that's pretty self-explanatory. On one hand, luminosity refers to something as light. So it's a measure of the total light output. And it is expressed in the unit of watts. We measure luminosity by measuring apparent brightness and then applying inverse square law. So as this was explained in the chapter on light, uh, as the distance increases, the brightness decreases by inverse square law. So we uh, apply it in reverse and calculate how bright as the star would be based on how bright it looks to us right now from our distance. Um, Another way of expressing luminosities is in comparison with the luminosity of the sun. So for example, luminosity of the sun is 3.9 times 10 to the 26 watts. Taking that as a unit, uh, the range of luminosities of all the stars is the lowest is 10 to the negative 4 or 1/10,000th of the sun's luminosity, and the maximum ones have a million times the luminosity of the sun. When it comes to magnitude, there is an apparent magnitude. Apparent magnitude is how bright the star looks, and that is a function of two things. One, how bright the star actually is, and second, how far it is from us. So that is the apparent magnitude. But there is another number which is called the absolute magnitude, and there the effect of the distance is removed by actually doing calculations in such a way that how bright the star would look if we were 10 parsec away from the star. So that gives a better measure of the star's energy production. Here is an example where the apparent magnitudes of various stars in the Pleiades constellation in the Pleiades is being shown. Next topic is temperature and color. How do we measure the temperature of stars? Well, we do that by uh, using the color and the wavelength of the light coming from the stars. So it has been found that um, that very low temperature stars it looks to me like the diagrams and the explanations might have gotten reversed here. Actually, it is not reversed. Right. So this is a chart that shows the intensity of emission. So when a star emits light, it emits light in various wavelengths, and those wavelengths can be plotted here according to intensity. And as you can see, um, the low temperature stars emit most of their energy in the infrared range. So most of it we cannot see. Some of it overlaps with the red color of the visible light. And so these stars look red. Now, stars which are in the range of 5,000, 6,000 Kelvin, uh, their peak is in the middle of the visible range, and the mixture of colors makes them look more yellow or white. And then there are the extremely high temperature stars, and the peak of their chart of their uh, wavelength intensity chart actually lies to the left of the visible range. And because of that, if you can see the slope here, you can clearly see that the maximum intensity is that of the violet and blue colors. And because of that, this is what the stars look like. So by analyzing the color of the stars in more detail, we are able to determine their temperature. Not only that, but according to the color and according to the temperature, the stars have been classified. All right, stellar classification. So the classes of stars are denoted by alphabets, and these alphabets are O, B, A, F, G, K, M. One way to remember the sequence of letters is oh boy and F grade kills me. So how was this classification of stars done? Well, initially, all the stars were photographed, and based on various factors, they were classified using letters from A to O. But then later on, the connection between the color and temperature was discovered. And so then it was rearranged according to the temperature, and also duplicate classes were removed. And so it was left, we were left with these 7 letters, O, B, A, F, G, K, M. But now 2 more classes have also been added, L and T, which are very low temperature classes, but because of our improved technology, we are able to see these stars also, which are very dim. So this stellar classification is based on temperature, and O stars are the brightest and hottest stars, highest temperature stars, whereas as we move to the right, those are low temperature stars. There are other characteristics of stars which appear at different temperatures. You can see these absorption lines. There are some absorption lines that are more present uh, in the lower temperature stars in this diagram. These are the spectra of different stars, and from bottom to going up, they are in increasing temperature. And so you can see at the lower temperature, there are several uh, absorption lines that are present. As we go higher, those absorption lines go away and new ones appear. So these are helpful in identifying the spectral class. Further on, there is subdivision between the OBA, F, GKM classes, and the further subdivision is by adding a number to the letters. So there's A0, A1, A2, A3, A4, A5, starting from A0 being the hottest. Flowchart for finding key properties of a nearby star. So this shows you the sequence of steps by which we get all the properties of a nearby star. So first we start with parallax and apply this formula. D is 1 over P, which gives us the distance. Then we measure apparent brightness, and we input the measure of brightness and the distance into this formula, and this comes out with the luminosity. And the luminosity is fed into this formula. It has several variables, as you can see. Those other variables are received from here. From the spectrum, we can find the spectral type such as O, B, A, F, G, K, M. And by finding the spectral class, we can find the temperature and feed it into this formula. So by feeding the luminosity and temperature into this formula, we can calculate the radius of the star. The spectrum also helps us figure out the chemical composition of the star by looking at the absorption lines. So um, a chart was designed to display the properties of the different stars. And this chart has been really useful in classifying uh, and identifying similarities and differences between stars. So on the x-axis, there are the spectral type, starting from hottest at the left to uh, to coolest at the right. And then on the y-axis is the luminosity, going from low luminosity to high luminosity. And so by making a dot for each star based on its spectral class and luminosity, it was found that those dots uh, congregate in certain areas. And especially there is a diagonal line that runs from the top left to the right bottom. And that one is called the main sequence, and most stars are in there. However, some stars congregate in other areas. And these two areas at the top that you can see, those are called giants and supergiants because those are quite big. And then the ones below the main sequence over here, they are quite small in size. So they are called dwarfs. And they are called white dwarfs or brown dwarfs, depending on the temperature. So this HR diagram is very important to understand, to be able to understand the characteristic of a star if it is present in some place. We should be able to understand what its properties would be. Or if you are given that it is a brown dwarf, then you should know where it will be placed in the HR diagram. If it is a blue giant, then where will it be placed in the HR diagram? This is another version of the HR diagram, which is luminosity against temperature. And when we draw it this way and draw these diagonal lines show the increase in size of the star. There are some other details and sections which I'll leave for you to study. However, this is something that I want to mention. There is another kind of classification uh, which is done, and this is not the spectral classification. These are luminosity classes. So according to how bright the star is, there is a classification that is made. And those classifications are the main sequence stars, subgiants, giants, bright giants, less luminous supergiants, and luminous supergiants. These are the luminosity classes. Now, what happens is that some stars are so far away that uh, we cannot measure their distance using parallax method. So what we do is um, we use spectroscopic parallax. And it has been observed that uh, the the wideness, the width of the absorption lines depends on the luminosity and the radius of the star. So a supergiant star has a smaller width of absorption lines, whereas a main sequence, which is a denser, high pressure atmosphere, there the width of absorption lines is more. So looking at those absorption lines sometimes helps us figure out if it is a main sequence star or if it is a supergiant, and so on. It helps us figure out the luminosity class. So when we can't measure the distance using parallax, then we use spectrum for three different things to find the spectral type, the chemical composition, and the luminosity class. Okay. Um, the spectral type gives us the temperature as well. We can combine the luminosity class and surface temperature on the HR diagram. The surface temperature and luminosity class give us the vertical and the horizontal coordinates on the HR diagram. So we can figure out where it lies. And then from that, we can figure out the luminosity. Then the luminosity and the temperature are fed into this formula to figure out the radius. On the other hand, the luminosity combined with the apparent brightness allows us to calculate the distance. So this is called the method of spectroscopic parallax for determining the distance of stars. All right, so here we'll take a little bit of detour. Um, and start talking about binary stars. So many of the stars that we see in the sky are actually binary stars, two stars circling around each other. For example, here is one. As seen from the Earth, the two stars that make up the binary system are separated by less than 1/3 arc second. The images, anyway, they look like one, but they are actually two. So this is a binary star system. So in the binary star system, the two stars uh, circle around a common center of mass. And the positioning of the center of mass is in such a way that it is closer to the more massive star, such as this. The center of mass of the two children is closer to the bigger kid. In the same way, in a binary star system, the both the stars are actually circling a common center of mass. But as you can see, the more massive star has a smaller orbit, whereas the less massive star has the bigger orbit. This is the mass luminosity relation. As the mass of the star increases, the luminosity also increases proportionately. Coming back to uh, the binary star systems, how can we find the different properties of the binary stars? So the next property of the binary system would be the velocities with which the stars are moving. So that is found using the Doppler method. So as we have learned in the chapter on light, in Doppler method, the absorption lines move depending on the direction in which the star is moving. There's either a red shift or a blue shift. So the same thing happens here. At some point of time, one star is coming towards us and the other star is moving away from us. So these lines split. One moves to the left, the other moves to the right. And by studying those at different times, we are able to determine the velocities of the stars in the binary system. Here is an example of a real life spectrum where we can see the splitting of the absorption lines and how they look like. Some of these binary systems could be eclipsing binaries in such a way that one of the stars might eclipse the other star from our point of view, and then the overall light output of the system decreases. Um, and by measuring those differences of the light output, the negative spikes, the distance between the time between the two negative spikes is what allows us to determine the orbital period. This is called a light curve, and there's other things that we can figure out from the light curve, such as if the central star is quite big, then there is a sort of a plateau in this spike, and uh, the the time of this plateau is the time to cross the disk of the large star, and that helps us calculate the radius of the bigger star. Sometimes these light curves are rounded. When they are rounded, that is a signal that the central star is being tidally stretched by the companion star. So these are some of the methods that we use to determine the properties of the stars and of the binary systems. There is a pretty good summary of all the points in this chapter. So please study them. And thank you.